Continuing with section 1-1, Mathematics and Problem Solving, I'd like to go through a problem that's presented in your textbook. This problem is titled Solve a Simpler Problem and Make a Table. So this is one example of another problem-solving strategy. The strategy that we're going to use to solve this problem is making a table. And it's possible that you can solve this problem with other strategies, but we're just going to go through and demo how to use that strategy by solving this problem. So starting off, step 1, understanding the problem. The directions here are pretty brief. It says find the perimeter, and we can see that we have multiple triangles stacked together, and we're asked to find the perimeter of this overall structure. I'm changing the problem slightly from what's in the school book page just to make it a little more general, but after this you should be able to follow the school book page in your textbook. So the first thing I want to notice is that the triangles appear to be regular. Regular polygons, for example, like a triangle, it means that all sides are equal length. So if I'm looking at any one of these triangles, if I know one side, maybe the side length I'll call S, then I know that the other two sides are also S. And that matters in this problem because we're talking about perimeter. I like to say perimeter is the distance around the rim, and we can remember that because the word rim is in perimeter. So if we're looking at the distance around the rim, then the goal for this problem is to find the distance along this edge, continuing along the bottom edge, up along the right side, and then back around the top. So we want to know what is the distance traveled if we walk around the rim of all of these polygons stacked up together. If we just had one polygon, then we could see, if we had one triangle, we could see that the perimeter would be equal to S. So for this one triangle, perimeter equals S plus S plus S, or 3S. But when we stack them up, we lose a side. For example, when we're seeing the first triangle stacked next to the second triangle, we would not count this middle side between them when we count the perimeter sides, because this side is not on the perimeter. So when we're stacking all of these up, we want to keep track of how many sides are actually on the perimeter. It's no longer 3 sides from each triangle. It's going to depend on where the triangle is. For example, this outside triangle, 2 of the sides count, but this one side does not. But for an inside triangle like this one, this side of the triangle is not on the perimeter, and neither is this one. So only one side of this triangle is on the perimeter. So understanding the problem, I think we get it fully. We're trying to find a way to calculate the edge of the perimeter, and it's true, we could just go on and count each of the sides. So let's do that. I'm going to highlight each one and we'll count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sides. So if I knew that one side was maybe 1 inch long, then I know that there are 14 inches to travel around the entire perimeter because we just found 14 sides. So as far as understanding the problem, we want to find the perimeter of all of these regular polygons stacked together. Our plan is to use a table Now we know the answer. We just found the answer by adding up all of the edges, but we want to use one of our problem-solving strategies because remember that solving these math problems is about building our problem-solving abilities. So our plan is to use a table. The way that we're going to use a table is we're going to look at how the number of triangles is related to the perimeter. So this is the table that we're going to use. If I had exactly one triangle, the perimeter was s plus s plus s, or 3s. If I have two triangles, let's draw a picture there. I have one triangle here, and then my second triangle here. I can count the sides, 1, 2, 3, 4 sides. So that would be like 4s. What if I have three triangles? Then I have 1, 2, 3, 4, 5 sides. So 5s. What about four triangles? Count the sides, 1, 2, 3, 4, 5, 6 triangle sides. As we're looking at our table, maybe we're starting to notice a pattern. The number of triangles is increasing by 1. The perimeter is increasing by 1 more s. So with one triangle, we had 3s for the perimeter. Two triangles was 4s. Three triangles was 5s. Four triangles was 6s. So we're seeing maybe a relationship here between the number of triangles and how many sides make up the perimeter. For one triangle, if I were to take the number of triangles and add 2 to that, I would see 3. For two triangles, if I add 2 to that, I would see 4. Three triangles, add 2 to that, I would see 5. Four triangles, add 2 to that, I would see 6. So what I'm seeing is for whatever number of triangles, I'm going to call that n for the number of triangles, the perimeter becomes n plus 2 times whatever that side length s was. So we used a table to help us see a pattern. We created our table and then looked at it to see the pattern, and that's the carrying out the plan step. And now looking back, we can generalize the solution to this problem. Although we already knew the answer was 14 of those sides added together makes the perimeter, we want to try and see if our new shortcut will work. Our shortcut says count the number of triangles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For 12 triangles, the perimeter should be 12 plus 2 times s. So 14 times the side length. And that's exactly what we said. It should be 14. Let's try another problem that requires some problem-solving strategies. For this problem, we are tasked with completing a magic square. So a magic square looks like this square that's been partitioned into 9 smaller squares. And it's magic because if we add along a diagonal, or if we add along a vertical, or if we add all the numbers on a horizontal, they should each come out to the exact same sum. So we are tasked with putting numbers into each of these small squares so that it is a magic square at the end. Anybody who's ever played Sudoku might think that this feels familiar. It's a little bit like Sudoku, but slightly different. So our goal here is to fill in the numbers. We get to use the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you like guess and check, maybe you start by plugging them in. Let's try it. does this work? In the top row, if I add these numbers together, I get 6. In the next row, if I add these numbers together, it is not equal to 6. So I know I did not place the numbers in the positions correctly. So guessing that way isn't going to help us. In fact, you can guess as much as you want. You might get fed up because every guess you make, you have to check the 3 vertical sums, the 3 horizontal sums, and the 2 diagonal sums. So although we could try guess and check, that's going to make us feel maybe a bit hopeless. So instead, let's devise a plan. Let's think about what has to be true in this square. Whatever number I put in this first box, the second box, and the third box, it's going to add up to a sum. And whatever number I put in these middle row boxes has to add up to the exact same sum. And the same thing for this bottom row. If I did have the numbers in these boxes, I could add them up and I would see that each row comes out to the same value. But also, looking at the way that we've drawn this out, we've used all 9 numbers in one of these 3 sums. So we used 3 numbers in the top row, 3 numbers in the middle row, 3 numbers in the bottom row. Which means if I were to add up the 3 sums together, I'm essentially adding up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. And maybe I'm not adding them up technically in that order, but somewhere in this magic square, a 1 is there, a 2 is there, a 3 is there, a 4 is there. I've got all of my digits sorted out into that magic square. So I know that this sum of 1 added up all the way up to 9 is going to be equal to s plus s plus s. Or I could write that as 3s. And if we watched the first half of the 1-1 videos, we should be able to calculate this pretty quickly. We know that that sum is equal to the first plus the last term times the number of terms, and we know we're going to divide that by 2. That comes out to be 5 times 9, which is 45. So we have 3s is equal to this sum, which we just said was equal to 45. So we know 3s is equal to 45. And that's important because if we know what the sum is, then we can start to make guesses about what 3 numbers need to appear in one row. For example, 1 plus 2 plus 3, that gave us 6. If the sum should be 6, then we know those 3 numbers get to go together. But if the sum is not equal to 6, then we can't put 1, 2, and 3 in the same row, or the same column, or the same diagonal. So let's find out what that sum is. We'll divide off the 3 so that we can see s is equal to 15. S being 15 is helpful because now we know that we should look for triples, so 3 numbers, that add up to 15. That's going to say don't put 1, 2, and 3 in the same row. Don't put 1, 2, and 3 in the same column. Don't put 1, 2, and 3 on a diagonal because they only added up to 6, and that's not enough. So we're going to look for all the triples that add to 15. Now, if you start to just pick numbers that you know will add to 15, you can actually cause some confusion with yourself because you might overlook one of the triples that you're going to need. So we're going to use a systematic list. We're going to make a list starting off with the largest number because it's easier to add smaller numbers. So we're going to make a list starting off with 9 And then we're going to pick the next smallest number that we can add to that so that we can still add two numbers. What do I mean by that? If I were to plug 8 in right here, well, 9 plus 8 is already 17. That's too big. So I know I cannot use 8. 9 plus 7. That's also too big. 9 plus 6. That's also too big. But what about 9 plus 5? That's 14, which is perfect because then I can use a 1 to make a 15. So this would be my first ordered triple. I'm going to continue using the 9 in front, and I'm going to decrease my middle number by 1. I should not increase the 5 to a 6 because I already know 9 and 6 can't go together because they're already 15 as it is. So I'll decrease my 5 to a 4, which would allow me to use a 2 for my third number. And I'm going to keep doing that until I run out of numbers. So then 9 plus 3, where I use 3. Oh, that's not going to work because I don't get to use any one of my digits multiple times. So I know that as far as 9 goes, there's only two possibilities. I can use 9, 5, and 1, and I can use 9, 4, and 2. These each give me a sum of 15. Now that I know all the sums that involve 9 to get 15, I'm going to move down to 8. Now 8 plus 7, that's already too big. So I'm going to switch over and go one lower, 8 plus 6. And then if I use 8 and 6, I can add 1 to that to get myself to 15. We're going to keep 8 as our first number, decrease the 6 to a 5, increase the 1 to a 2. This is another sum of 15. We're going to keep doing this until we arrive at a problem like using the same digit twice, for example. So what about 8 plus 4 plus 3? Yep, that's also 15. What about 8 plus 3 plus 4? Well, it does work, but guess what? We already used that one. So we're not going to include that on our list because we don't really care which order the three numbers are in. We just want to know what three numbers can be added together to get 15. So we finished our list of 9s, we finished our list of 8s, which means we can move on to the 7s. Now, I won't consider 7 plus 8 or 7 plus 9 because all the triples that involve 8 are already listed out. All of the triples that involve 9 are already listed out. So we're kind of working our way down this list of numbers. Once I cross off the 9, I won't use it anymore. I won't use the 8 anymore. We're working on 7 with the numbers smaller than 7. 7 plus 6 would give us 13. So it's okay to use 7 and 6 together. But if we have 13, we need 2 to get us to 14. So 7 plus 6 plus 2 gives us 15. We would not be able to use a 1 with that 7. So we're going to keep the 7 up front, decrease the 6 to a 5, increase the 2 to be a 3. So 7 plus 5 plus 3, that's also 15. See if we can go one further. 7 plus 4 plus 4. Nope, that doesn't work because we have two 4s in there. So we know that our list is done. All of the 7s have been completed. We'll cross off our 7 and continue making our list with 6s. So 6 plus 5, that's 11, which means we would need 4 more to make ourselves at 15. We can try to continue that going down. 6 plus 4 plus 5. Oh, well, we already have that one, so we're not going to duplicate that twice, which means all of the triples involving a 6 are complete. Next, we'll look at 5 compared with any other numbers. So 5 plus 4, that's 9. In order for this to be 15, we need to add 6. But 6 is already crossed off. We're not allowed to use it. That tells us that we cannot start with 5 and pick two smaller numbers to add to 5 to get 15. So we have found all of the ordered triples. Because we used this systematic list, starting with the largest number, working with the largest pair, and then continuing that process down the list, we know that we've covered all possibilities. And if you look at the number of sums that we have 1, 2, 3, 4, 5, 6, 7, 8 sums. And that matches perfectly with 3 verticals, 3 horizontals, and 2 diagonals. So we have all 8 triples. We just need to figure out how to place them into the appropriate squares. Now the next part of this is kind of tricky. What we need to do is figure out which of the triples go in each of the rows, each of the columns, and the 2 diagonals. And to do this, we need to look at how popular some of these numbers are. For example, you can see that the number 5 shows up 4 times. That's a pretty popular number. So to make this more clear, let's create a table where we list each of the numbers that we're allowed to use and how many times they show up inside of our list of sums. We just said that the number 5 shows up 4 times. So let's take a look at some of the other numbers. Oops, I just erased a 5. Put it back. What about the number 1? I see 1 here, and I see 1 here. So it looks like the number 1 shows up twice. Let's look for all the times the 2's show up. So I've got 2, 2, 2. We have 3 appearances of the number 2. The number 3 shows up 1, oh, there we go, 2 times. The number 4 shows up 1, 2, 3 times. We have the 5. Oops, I said 3 and I wrote 4. The number 6, let's see all the places 6 shows up. 1, 2, 3 times. The number 7, 1, 2. That's 2 times. The number 8, 1, 2, 3 times. And the number 9, twice. So looking at our table, we can see that 5 is the most popular number. And that's useful because one of the squares in our magic square gets used the most. This top square, for example, is used in the sum from the first row. It's also used in the sum of the first column, and it's used in the sum of this diagonal. But that's only 3 different sums. What about this middle square? How many times is that used? Well, 1 row, 1 column, and both diagonals. That square needs a number that can be used 4 times. So I know that 5 has to go into this center square. We know that 5 is contained in a few different sums. So let me highlight those for us. And what we need to do is make sure that we apply the other 2 digits, right, on the diagonals or in the row or in the column so that they work happily with all of the other sums that we're going to calculate. So we know 5 has to go in the middle. If we look back at our table, we might notice that the number 2 shows up 3 times. The number 4 shows up 3 times. The number 7, oops, I meant to circle the 6. And the number 8. These 4 numbers, 2, 4, 6, and 8, they each show up 3 times in our list of sums, which means these numbers belong on a corner. Remember, we said the corners are involved in 3 different sums. It doesn't matter which corner we place the numbers in. We can totally sort it out to make it work however we want to pick it. But let's start with the 2. I'll take the 2 and put it in this top corner. Now that I have a 2 and a 5 in this diagonal, I know what number has to go on the bottom right corner. I just need to look to my sum that involves a 5 and a 2. And then I'll know that it has to be the 8 down here. We know 4 and 6 belong in the corners, but 4 and 6 would not work in this corner because we need this diagonal to add up to 15. That requires it to be an 8. Let's go ahead and pick another number to go in our top right corner. It can either be a 4 or a 6. Let's pick a 6. If I pick a 6, then I can look at the 5 in the center and say 6 plus 5, which sum involves that? It would have to be this, 6, 5, and 4. So we know that the other 4 would have to be in this bottom diagonal. We're going to keep going through that and fill in the missing pieces. So I'm looking for a sum that involves a 2 and a 6. A 2 and a 6. That's this one right here, which means the number between the 6 and the 2 on the top row has to be a 7. What about a 2 and a 4? Well, I see a 2 and a 4 right here, so the number between them would have to be the 9. What about a 6 and an 8? That would have to be this sum right here. The number between them would have to be a 1. We just filled in the 3 squares in the center column, but let's make sure that adds up to 15. 9, 5, 1. Yep, that's 15. We have 1 square left. We're looking for a sum that involves a 7 and a 5, or a sum that involves a 4 and an 8. Either way, you're going to find that it needs to be a 3. And this magic square has every row adding up to 15, every column adding up to 15, every diagonal adding up to 15. So for this problem, we started off by making sure we understood the problem. We took the time to look for a plan, which was find all of the triples that add up to 15. We made a list so that we could find them all. We carried that out. We found the solution, but now we have one last step, and that's looking back. Now, sometimes looking back is about finding a general way to do the problem faster, but sometimes looking back is this the only answer to the question? Is it possible for us to have made a different magic square? We know that 5 had to be in the center, but we did have 4 different choices for the corners, and I arbitrarily picked 2 to start with, but you could have picked a 4 to go in the top right corner. You could have picked left corner. You could have picked a 6, or you could have picked an 8. So it does not have to be 2 up here in the top left corner. It just needed to be one of the numbers that showed up 3 times. So it's possible for people to have different answers for this magic square and for them to still be correct.